here today Fernando Guadalupe Brandão. He is the head of quantum algorithms at Amazon Web Services, AWS, and the professor of theoretical physics at Caltech. Previously, he was a visiting faculty at Google's Quantum AI Lab, also a researcher at Microsoft, and also a reader at University College London. Before that, he was at ETH and also assistant professor at my beloved Federal University of Minas Gerais. And he got his PhD from the Imperial College London. And today, he's here to talk about quantum error correction with concatenated bosonic qubits. Fernando, floor is all yours. Thank you very much for it.
Thank you for inviting me, Chris. Hi, everyone. It's nice to be here. First time in Chapman, so I'm like an hour away if there is no traffic. Today there was no traffic, so I was very happy. And I want to tell you about some work that we've been doing at the AWS Center for Quantum Computing, which is some research institute from Amazon on Caltech campus. That's our building. That's the mountains nearby Caltech. And our long-term goal at CQC is to eventually build a quantum computer that can bring value right to society, to Amazon customers. But I'll tell you the progress that we could do so far towards this very long-term goal. All right, so So to start, what do I mean by these useful quantum computers, right? So we would like to build quantum hardware that we can run potential interesting applications of quantum computing. This can be in cryptography, for example, breaking RSA, right, using Shor's algorithm. Can be in chemistry, simulating some interesting and complex molecules that we cannot do with our current methods. It can be in optimization, for example, adiabatic optimization, or other algorithms and so on. But where we are versus where we want to be, right, to run these interesting applications. So where we are today, and I mean like the quantum community, right, in general. And there's many different experiments that people are trying to build to do it, and I'll tell you the one that we are doing. But everyone is roughly like from tens to hundreds of qubits, we call physical qubits. And in the model of quantum computation, right, you have these qubits and you apply gates on them to that, a lot of these gates create one quantum algorithm. The error rate, right, so is between 100 and 1,000, right? So every 100 to every 1,000 gates, one of them is like, there's an error there. And where we like to be for these applications, right? So many people do this kind of work. So we also did some paper where we just some review on quantum algorithms where we try to estimate, right, what it would take. And then you find that we need from hundreds to thousands qubits. So that's not too far, right? To say, oh, maybe that's great. But if you think about how many gates you need, you quickly realize that the error rates have to be something like 10 to minus 10 to 10 to minus 14, right? So there's like a huge gap, right? So because we want to run some interesting algorithms, right? These algorithms have to have a lot of gates, billions of gates, right? And because they also have thousands of qubits, you end up having error rates of 10 to the 12, 10 to the 14. So it's like a huge gap, right, that we have to bridge. And then the question is, how can we bridge, right, this kind of 11 orders of magnitudes that we have to, if you want to build these useful quantum computers. And if you didn't have any good idea, we should just give up, right, because it's 11 orders of magnitudes. But we know, right, since like 30 years ago, that at least in theory, right, we can do what is called quantum error correction and try to bridge this. And that's kind of the main challenge of quantum computing these days, right? So how can we get quantum error correction, which will explain more what it is, to work in practice, right? So no one could do that so far, but that's a big like challenge for the field. Okay, so what is quantum error correction, right? So now we have our qubits, right? They're the physical qubits. They're these two-level quantum mechanical systems. And now the idea of error correction is that we want to use many physical qubits to collectively encode one qubit that we call the logical qubits. And then because we can use some redundancy in the encoding, all these physical qubits can collectively fight noise, and the logical qubits error rates can be much, much lower than the physical qubit one. And you can do that for qubits, and you can do that for gates as well, right? So in the end, you can think about logical gates applied to the logical qubits, which will be built from many physical gates applied on these physical qubits. And collectively, you can engineer things such that the logical gates error rates will be much smaller than the physical gates error rates. Okay, so
much means how much?
So our goal is like 11th order of magnitude lower, right? Where we are today, I'll tell you in a few slides. It's very modest, but we start to see some improvements. So there's been a few, like many interesting experiments. So for example, like trapped ions, like this paper on superconducting qubits. There's results from Google, right? From like ETH, some from IBM, and I'll tell you the experiments that we do at AWS are also superconducting qubits and neutral atoms, right? Really kicking off many interesting experiments from Harvard and other places. I'll tell you more detail, but just because you asked, right? So where these experiments are today? Well, today you can have a logical qubit, which is like slightly better than the physical qubits. That's what you can do, right? Or depending how you quantify it, it's a factor of like 2 to 4 better than the physical qubits, the error rates. So very minor, right? But at least we start to see some progress. But I'll tell you this number soon. All right. So, but now there's a big question that this one, right? Even before building the experiments, we can address, which is what is the overhead of this, right? What is the overhead of error correction? So error correction works is great, but we need many physical qubits for one logical qubit. So the question is how many physical qubits will you need, right? If you want to have go from 0.1% physical error rates to 10 to the minus 14 logical error rates, right? And this number I use because this number, for example, is what you would take if you want to break RSA, right? With 2048 digits, right? Like if you want to run Shor's algorithm. Okay, and I'll tell you how many physical qubits, unfortunately a lot, right, from what we know today. How we usually think about error correction, right? There is actually, for a long time, there was only one code, this one I'll explain, but now there's all these like different codes and different ideas appearing. So it's a very vibrant field right now, like theory of error correction. But it's still a very important idea. It's what we call the surface code. So this is a quantum code where you put qubits on a square. Your physical qubits, right, which will encode the logical qubits, are these dots here, these kind of reddish dots. And this you have extra qubits, which are these blue qubits. And these blue qubits is what we call ancilla qubits. They are there such that we can measure them and we can infer, you can correct the errors on the blue dots, right? So now you can think of the logical qubit living in the blue dots and the red dots, in the red dots, and the blue dots are auxiliary qubits just to correct the errors in the red dots. So there is a parameter of this code, it's a family of codes. There's the distance of the codes. So it's a d by d square. So you have roughly 2d square qubits, right? For a distance d surface code. I won't explain detail, but the way the error correction works is that you have to measure 4 body Pauli operators here. So you measure like x, 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 x here, x, x, x everywhere, and you also measure z, z, z here, right? So z, 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 and x, 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 and then you can see they all commute, and then you can see that the grounds, the protected eigenspace, right? When all these Pauli observers have eigenvalue 1 is 2-dimensional, and this encodes exactly 1 logical qubit there. So this is a idea from Alex Kitaev, right? Also, like 25 years ago. And what you can do, you can estimate how good of a memory this is. You can run some simulations, right? You put some error model here, and then you end up in this kind of expression for the logical error rates. So this I denote the logical error rate, right? This is the error rate of the logical qubit that we encode using the distance d surface code. This 1/lambda parameter in the simplified error model is given by the physical error rate, right? So suppose that P is the physical error rate of all the gates and all the readouts and everything, right? They're all the same in the simplified error model. Then the logical error rate scales as the physical error rate divided by some constant that we call the threshold of the code. Is a property of the codes. It's like 1% for the surface code, roughly. And then this exponentially decreasing with the distance of the code. So the bigger the distance, the smaller is the logical error rate, and this drop-off is exponential in this distance. up to +1/2. So that's great. The two things, right? Great, the logical probability of error decreases exponentially. Yes.
Is this related, like the D, is it related to the Hamming distance on the classical setting?
It is, yeah. So what you can show is that this code could detect up to D errors, but then can only correct, D +1/2, right? Because yeah, because for example, you can have a string up to here, right? You can detect the string up to here, right? But then if you have the code words, right, the string coming from here, you will be able to correct necessarily, but you could still detect there.
Yeah.
Right. So, and another important thing is that this doesn't always work, right? So only when your physical error rate is smaller than the threshold, right? And it better be like much smaller. This is effective, right? And that's why we haven't seen many QC experiments until recently. It's just because the error rates that we had in the lab in all these platforms, they were just above the threshold. So there was no point in doing error correction, right? Experiments. You just have actually a logical qubit to have a worse error rate than your physical qubits, right? Or your physical gates. But now the experiments are good enough that we are below this threshold. So now it makes sense to scale. And once you scale, you see this kind of exponential improvement. What is the state of the art? Is to have lambda equals 2. Okay, so this was done by Google in 2024. They ran exactly the surface code with distance with d equals 3, d equals 5, d equals 7. And they saw when it goes from 3 to 5, the logical error rate dropped by a factor of 2. When they went to 5 to 7, it dropped again by a factor of 2, right? Which means this lambda parameter equals 2. And very recently, also in Rydberg atoms at Harvard, they found lambda roughly 2. They could not repeat many times, right? Because error correction, you should just keep measuring, like this Pauli that I mentioned, over and over again, and the information stays there, right? The qubit stays there. But Rydberg atoms, they just fly out, right? You lose the atoms. So they could not repeat many times. They repeat like 4 times, and they had to stop. But still, they could infer roughly lambda equals 2. Okay. Now, going back to the question that I asked before, right? So how many qubits it takes then? What is the overhead to get to this like useful regime, right? So suppose lambda is 10, right? It's still like 5x better than the state-of-the-art experiments. And suppose we want to get to logical error rates of 10 to the minus 14 to break RSA, for example. Then you can use this formula and get that you need distance 25 for your surface code. And then you can use this like 2 times 25 square, right? That I told you. And you find that you need like, 1,250 physical qubits per logical qubit, right? So, and that's a lot, right? So it's given that, today we can do hundreds of qubits, maybe getting close to 1,000 in some platforms, that's a lot, right? So error correction works, but the overhead is quite steep, right? That's kind of the message, right? So if you want to have in the end thousands of logical qubits for the applications, as I mentioned, this leads to kind of like millions of physical qubits that you need. And this is like the challenge of quantum computing, right? How to scale these experiments that we have today, ions, superconducting qubits, Rydberg atoms to millions of qubits, right? That's quite challenging. It's something that is very exciting, but it's quite challenging. All right. So the research that we'll be doing, right, and what some of the results I'll tell you, we try to address this question, which is there a more efficient way of doing error correction, right, than just getting lambda to be like 10 or something like that and just scale the surface code, right? Is there like something maybe more efficient that you can do? All right, so let me tell you some approaches that people are considering, right? And I'll tell you more about one of them that we're doing. So one observation, one thing that you can definitely do is just keep improving the physical errors, right? Which means keep increasing lambda, right? This lambda parameter. So this lambda is some aggregate parameter of how good all your components are there, right? Your gates, your 2-qubit gates, your single-qubit gates, your readout, your state preparation. And again, today we are lambda equals 2, right? I think lambda at least 10 we should try to reach before scaling. Otherwise, it's right. You just have to scale too much. As I show you, lambda is already like the overhead is 1,000, right? But now, because of this formula that I showed you before, right, which goes as distance plus 1/2, and the number of qubits here goes as d squared to d squared. What you can see is that if you increase lambda from 10 to 100, which will be pushing the error rates a lot physically, right? Like reducing them, like 10x more. you have a 4x overhead reduction, right? So you know, you have a 10x improvement in physical error rates, but only a 4x overhead reduction sum. And if you keep going, now you go from 10 to 1,000, you improve a lot, right? So it's very unrealistic, I think, to think that we'll be able to get to these physical error rates. Then you only get, no only, but a 9x overhead reduction. So what this shows is that if you're above the threshold, there is no point in doing the experiment. If you're just below the threshold, the overhead is terrible. You should not try to do it. If you're 10x below the threshold, okay, it's still a lot, but it's reasonable. And below that is diminishing returns, right? So this gives like, you know, this roughly gives where the surface code should be able to give. But if you want more, right? So actually recently, surface code, why we like it? Well, the threshold is high and you only need gates on a two-dimensional lattice, right? So this is very good for experiments, right? Where the gates can only be applied between neighboring qubits. But now suppose you can apply long-range gates, right, between faraway qubits. For example, you know, in ions or Rydberg atoms, you can do that, right? Because you can just move the atoms around or the ions around, and you can do it. Then actually there is, it's called like quantum LDPC codes, similar to how you have like this classical low density parity check codes. And you can have overhead reductions with these long range gates over the surface code. Another approach, which is the one that I will talk about more here, is when you have what we call biased noise. So there is actually two types of error, right, in quantum mechanics. You can have bit flip errors, where, you know, a qubit, a 0 becomes a 1 and a 1 becomes a 0, right? That's just the error that we have classically. But because it's quantum mechanics, you can also have like bit flip error in the complementary basis, right? So a plus can become a minus. So it's a phase error, right? A 0 plus 1 can become a 0 minus 1. So one is an X Pauli error, the other one is a Z Pauli error. And, you know, like typically X is roughly the same. The probability of an X error is roughly the probability of a Z error. But suppose you can engineer your qubits in a way that the probability of an X error is much, much smaller than the probability of a Z error. Then actually what you can show is that the surface code, you can just fin it in one direction. So the surface code, you can think of, you know, one of the directions is correcting X errors, the other one is correcting Z errors. And if you don't need to correct a lot of X errors, you can have like a thinner surface code. And then you have a better overhead because of that, right? And I'll tell you some concrete things a little bit later. And finally, you know, people are also trying to a similar idea, but like with erasure errors. So here, like, you know, you want an overhead reduction, but you try to engineer it, creating your qubits in a way that the most dominant type of error usually is like, you know, some kind of loss mechanism, right? So it's just energy loss in your qubits that you can kind of, is a flagged error. For example, when your atom lose like a, you know, excitation, for example, you could emit a photon and suppose you can detect this photon. Then you know that a loss happened. This is called erasure error because you know that the error happened. And then you can use this information that you know to have much better decoding algorithms, right? So much better error correction. So then there is the kind of error that you can, you know, there is erasure, it's called E. There's a type of error that you cannot, if there are no erasure, it's called P. And this will work well if E is much bigger than P, right? So maybe I missed something, but I think I haven't, but these are like the directions, you know, where many people are trying, right, to make progress to see if you can do error correction in a more efficient way and really, right, not have to scale so much. Any question? Okay. So I will focus on this one, which is the approach. At CQC, we are also exploring this one. We have some experiments on this. This one we're very interested, but we're not building anything. IBM, for example, is building, right? It's trying to build this. And of course, Rydberg atoms is very well suited for this, right? And there's no experiments yet, but I think there will be soon. We at AWS have been trying these two approaches. And of course, you know, this everyone is trying, right? Just to get better lambda. It's a common goal. All right, so I want to focus on this one. And what is the way, right? So I want to tell you how we can create the qubits for which the probability of bit flips, right, X errors is much, much smaller than the probability of phase flips, right? And let me show you how you do it. And one way to do that is use like bosonic quantum error correction. So let me tell you what is the idea here. So this is the thing that I just told you, right? So for doing error correction, you can have many physical qubits, two-level quantum mechanical systems, and use them to encode one logical qubit. But the idea of bosonic error correction is say, oh, maybe there's something more clever that I can do. Suppose I don't have, usually anyway, we don't have a two-level system, right? In the lab, we have a system that is more complicated. And suppose we have like a harmonic oscillator, right? So it can just be, for example, like a cavity, right? With photons bouncing back and forth. Then you have like a bosonic mode there. This bosonic mode, in principle, have infinitely many levels, right? And you can say, oh, now I have all these levels, so maybe I can use them in a clever way to create a qubit, like a two-level system, a bosonic qubit, but that has some kind of inbuilt error correction properties, right? Or in this case, they can somehow correct X errors, right? In kind of in a hardware efficient way. All right. So there's a lot of work on these bosonic qubits, and I won't explain what these are. So this is one I will explain, the one we're doing. But I just want to mention that in addition to the one that I will explain you, and is the one we're focusing, there's other ideas for using this kind of bosonic modes to create, this bosonic qubits. And they all have a common theme, right? So there's a lot of previous work as well, very interesting work, like people at Yale, people at University of Paris, and so on. But all these previous kind of experiments, they had also one thing in common, which was they wanted to correct or suppress physical errors with just one bosonic mode, right? And that's great, but we know it cannot be the end of the story, right? Because with one bosonic mode, you won't be able to get this like 10 to the 14 error rates that we want. So the experiment that I'll show you is really trying to go one step further, right? So we want to start with this kind of bosonic modes, which should give some kind of error correction if we are clever, how we use it, right? So we get this bosonic qubit. But this bosonic qubit won't be perfect yet, right? Because, like, for example, there's only so much energy we can put here, right? So just this cutoff in energy gives a number of levels that we can access, right? And this number of levels just give a finite amount of space for doing the encoding, right? So you have to go beyond. And the way to go beyond, then you go to traditional error correction, right? You just take many of these bosonic qubits, we concatenate them, and then we have an outer code, like a surface code, for example, to create our final logical qubits, right? And then this indeed can have error rates as small as we want. And then the question is, okay, if you put things together, what will be the overhead, right? Is it better than just having this surface code? All right. So yeah, so concatenate the bosonic error correction. We want to correct some physical errors, right, using the bosonic mode, and in that way have a more efficient way, hopefully, of doing error correction. So what is the experiment that we did? It was, it's described in this paper from the beginning of this year. So we had a quantum error correction experiment using this concatenated bosonic qubits that I mentioned, and we realized these logical qubits in a superconducting circuit, and using this concatenated bosonic error correction. So this is a layout of the experiment. So in our experiment, we had like 5 bosonic qubits, cat qubits, and I'll tell you what they are. I haven't told you yet, right? So 5 of them. Then, as I mentioned, right, in error correction, we also did ancilla qubits, right? So we had 4 ancilla qubits, are those here. And they, in this case, they were really just qubits, right? Like normal superconducting qubits. The transmons, right? But this doesn't matter so much. It's just like a normal qubits. And because we wanted these cat qubits to correct bit flip errors, right? Like kind of in the hardware, we had some extra kind of auxiliary mode or auxiliary qubits that was correcting the X errors kind of passively here in a sense. This is called the buffer mode. I'll tell you what this is. So this is like a picture of the chip, right, that we built there. And this is the layout, right, with the same colors, right? So for example, for the bosonic modes, right, we need, for the bosonic qubits, we need a cavity mode, right? The cavity mode is this kind of big strip line cavity here. Everything was in 2 dimension. And then, like for this extra buffer mode, it will be this here. The transmons are very, very tiny. You cannot see them, but they're over here. I'll give you a zoom later. Okay, so just a little bit more about, right, how we did this. So this is like some microfabricated superconducting chip. And actually it's like flip chips. So we have 2 chips, so we glue them. Then, we had a top chip, which was made of aluminum. And then this is where we had like our qubits, right? The transmons, this buffer that I mentioned, some other couplers that we need to control the gates, all the nonlinear elements basically. But then for our bosonic qubits, for our cat qubits, we want them to be as good as possible. And there is a material which is better, which is called tantalum, where you can have like higher Qs there for it. So the bottom chip was this tantalum, and then we glue them together, and that's how we get our, this layout that I showed you before. All right. So what just in terms of the parameters that we achieve, right? So for our cat qubits, like this blue here, this is what we call like storage as well, and the T1 time, right? So the T1 tells you, right, the relaxation time of these qubits was around like 70 microseconds. So that's not great, like if you compare it to three-dimensional cavities, like microwave cavities, but for two-dimension, we had to put a lot of work to get it there. Our ancilla qubits, right, really qubits, not bosonic modes, they were around like 30 microseconds. They're just like, and that's kind of is the average of them, and that's average for like superconducting qubits as well. We can do much better, but that's what we could do. And we had to do very good frequency targets here, around like 15 megahertz for this to work.
And which temperature is this?
This is like 20 millikelvin.
And is it temperature dependent, these parameters?
They are. Although like so if you go to like 100 millikelvin, then these start to go down, right? But in the range where they are, like if it's between 20 and 30 millikelvin, they shouldn't change so much. T1.
Too much is how much? I mean, 20%, 50%.
So it should if you go to like 100, we don't have like very good expressions, except kind of empirically. If you go to 100 millikelvin, then it drops by 2. I think that's something that we do, for example. So we definitely want to be like a range of 20, maybe 30 millikelvin, not more than that.
Your ancilla qubits or what?
They're transmons.
Transmons. Okay.
They're transmons, yeah. Okay, so this I show you, right? So now let me explain, right? So as I mentioned, the cat qubits, right? Bit flip, X errors, they'll be suppressed by these bosonic cat qubits. I'll show you how. And now, okay, what is the concatenation that is happening, right? So in our experiment, because it was the first experiment, right? All X errors we just correct by the cat qubits. All X errors being corrected here somehow. I'll tell you how. But now Z errors are not corrected at all. So then the outer code, we only wanted to correct the Z errors, right? And what is so there's only one type of error that the outer code has to correct. So this means that we can use a classical code for that, right? And what is the easiest classical code? It's just the repetition code, right? Where, if you want to encode a 0, encode into many zeros, 0, 0, 0, 0. If you encode a 1, encode in many ones, 1, 1, 1, 1. And that's what we did. So the outer code is just a repetition code of distance 5. Okay, so how you work this X correction, right, for this cat qubits? So what you can show is that using this kind of buffer mode that I introduced, you can engineer things in a way that these cat qubits, bit flips, they become exponentially suppressed the more photons you have in your resonator. Okay, so we can have first, right, coherent states, right, in the resonator. These are like alpha, right? It's just a coherent state with phase alpha. And of course, you can have also coherent state but minus alpha, right? So they have the same mean photon number, alpha square, but there's a different phase here between them, right? So this, this will be some kind of like the Wigner function of this, alpha minus alpha, right? So one is on the right hand side, right, of the Wigner function, and the other one is on the left hand side. Of course, now you can also have superpositions of them, right? And that's why we call them sometimes cat qubits, right? You can have a superposition of alpha and minus alpha, and of course, a superposition with the minus sign.
And then what is restricting alpha value?
Say again?
What is restricting the alpha value? The value of alpha is restricted by what?
You mean like how far you can push it?
Yes.
I'll tell you. So in our experiment, there will be a balance between bit flip suppression and phase flip increase as a function of alpha, and we have to tune that. It's coming. It's a good question. Now, what you can show, and of course, the bigger the alpha, right? So first, they are not completely orthogonal, but they're almost orthogonal, right? So the overlap between them is exponentially small in 2 alpha square. And when alpha grows, right, this kind of, they become more and more like classical states, right? And the superposition becomes like these cat states, right? That's the reason for the name. Now, what you can show is that when alpha increases, because they become more classical objects and they are orthogonal, it becomes very rare, right, that a physical process can bring you from one to the other, right? So the probability of a bit flip, which means you go from alpha to minus alpha, you can show under the right conditions that it decreases exponentially with alpha squared. Okay, so that gives this kind of exponential suppression that we like in error correction, right? But we don't need to have to increase the distance. The mean photon number here plays the role of the distance, right, in the surface code. Now, to your question, what we can also show is that there is a price you pay, and that the phase flips of the scat qubits will increase, the z errors will increase when you increase alpha, but in a nice way. They increase linearly in alpha square. So what you're doing here is basically biasing the noise when alpha square increases. So you exponentially decrease the bit flip error rates by linearly increasing the phase flip error rate, right? So what is the game you have to play? Well, you see how big PZ you can tolerate such that you can still correct at the outer code. And then you see this gives you the maximum value of alpha square, right, that you can tolerate. And then this gives you like kind of how much you can suppress X, right? All right. And the point is that if you increase alpha, you have exponential you're exponentially noise biasing, right, your qubits. The bias between PZ and PX becomes exponentially small in alpha square. Okay, so we did try that right in the lab. Well, not myself, I'm a theorist actually, but people work with me that do the experiments. And this is like the initial states, right? Oh, actually I have to tell you something here. So this is like some initial cat state, right? Like alpha. If you don't do anything, it's just kind of spreading, right, in phase space. But now there is a trick that we can do. We can engineer something there such that this cat state is preserved and you have this exponential suppression stays there. What is this? For that, we use this buffer mode, right? So we have our cat qubit is this bosonic system, a harmonic oscillator, and then so the annihilation operator for it will be A. And now we engineer with another mode, another bosonic mode, a free wave mixing condition, in the sense that this bosonic mode loses two photons, like 2 photons of this one is converted into 1 photon of the other one, right? So it's kind of, right, so you need a nonlinear element for that. We use some kind of transmon, it's called like a ATS, asymmetric Frederick squid, but using those kind of nonlinear elements that we can do, right, with superconducting qubits, you can engineer this free wave mixing condition between these two modes. And then if you make the buffer mode very lossy, right, in the sense that it just loses photons very quickly, just, the kappa is big here, what will happen? 2 photons from this get exchanged by 1 photon of this, right? So 2 photons go here and it leaks very quickly, right? So then what happens is that you end up in a dissipative process, but where your bosonic qubit loses pairs of photons, right? Instead of just losing 1 photon at a time. Then you can do like a 2 photon drive here as well and get this parameter. And then you end up in some kind of master equation, which has these jump operators, A square minus alpha square, where this alpha depends on how much you're pumping the system with this 2 photon drive. Now, if you think, okay, which states are kind of dark states of these jump operators, right? A square minus alpha square. Of course, if you have a coherent state alpha, right, and you apply A, you get alpha back. If you have a coherent state minus alpha and you apply A, you get minus alpha, right, as an eigenvalue. So if you square, you see that both alpha and minus alpha, they are preserved, right? They are dark states of this. And what you can show is that this dissipation will bring everything into alpha minus alpha, and the probability of going from one to the other becomes exponentially small. Okay, so to summarize what we do, well, which was proposed actually in papers from Yale before, and then the first one to realize this and see the exponential suppression was a group in France from Lecter. He was and first one to Lecan, like in 2020. So that's what we use. We just try to engineer this dissipation such that bit flips become very, very unlikely.
In this particular case, you were considering 2 photons, but optimum alpha from the previous page, what is the optimum?
So in our experiment, the optimal, because in the end we want to, right, we have to balance like phase flip errors and bit flip errors, and what we can correct with delta codes was photon like 1.5 roughly.
1.5.
But if we can get better kind of T1 of the resonator, we can increase alpha, right? So we do think if you eventually wanna, there's future versions of experiment where we hope we can use like, alpha square of like 5 or something like this. Yeah.
Okay.
And people have tried alpha like, and we also have alpha up to 10, and then you get like seconds of lifetime for X. But then of course it decoheres very fast, right? Because the Z errors become very likely, right? So this is exactly the plot. So this is the mean photon number, right? So we look at the four resonators in our chip, right? We switch on these two photon dissipation there. As I mentioned before, right? So usually the T1 starts at like 70 microseconds, right? And then this is like log scale, and then you see this exponentially increase, right? When the mean photon number increases, and then when you're around like mean photon number 4, you have something like around like 10 milliseconds, something like this, right? Or 100 milliseconds. And we have seen up to like 10 seconds if you go, like to alpha square 5 or 6. And at the same time, we also see this linear phase flip, right? Increase, right? So the phase flip time, right? It should go like 1/x, right? Because it's the inverse of the phase flip rate. You see this linear, right? So this 1/x formula, as we expect, right? All right. So this is a bit technical, and it should be 45 minutes, right?
Yeah.
Yeah. So let me jump this.
Yeah, it's okay.
Yeah, let me jump this slide just for benefit of time. So I roughly show you, right, how we did that in the experiment, right? How we can correct X error by switching this photon dissipation, and then we have this knob, which is the number of photons here. When we increase, the bit flip probability gets exponentially suppressed, right? And you saw this exponential improvement, right, which starts with like 70 microseconds, and we can go up to 0.1 seconds, right, in this chip, for example. But how about phase flips, right, errors? And for phase flip errors, now we have to do, I mentioned the repetition code, right, the simplest classical codes. But now it's really active error correction, right? So you have to kind of measure some checks to find an error and correct them, right? So how the repetition code works, right? So suppose you have a Z error here, right, that you want to detect. What you do all the time is that you measure the parity between all the pairs, right? So you measure like XX here, you measure XX here, XS here, and XX here. How you do that? Well, you use the ancillas. So you apply C naught, right, between the ancilla and this, and between the ancilla and this, and you measure the ancilla. And then in that way you can measure XX. And then if there is, if there is this error, you find that there is a XX with -1 eigenvalue here and another one here, right? And once you find, oh, these two clicked, it means, oh, there is a Z error here, and then you can correct. So that's how it works, right? And that's what we did experimentally. So the experiment is like, you have to apply C naught gates here and try to detect this. Okay, so what is this, this efficiency that we're getting here, right? Still in a small way, but it's a good proof of principle, right? So we started, instead of using a surface code, right? We can just use a repetition code. So we just squash what I mentioned here, right, to align. Now we can only correct Z errors. So the surface code becomes the repetition code in these limits. And now X errors we correct using this bosonic mode, right? That's the idea.
Can you please go back to this?
Yes.
In this case, it is clicking only at Z. But suppose that there is clicking in two places. How would you understand which one is real mistake, which one real error, and which one is true result?
Right. So it's a very good question, right? So the code has distance 5. So it means that we can correct only up to 2 errors, right?
12?
2, right? 2, right? So for example, you have a Z here and a Z here. So then these 2, right? You say, oh, this one, there is a violation. This one, there is a violation, and then right? If you have like one here and one here, you also know, right? Because this 2 would click and this 1 would click. But now if you have 3 errors, then you fail already, right? So that's this thing. A distance D code, you can correct, at most D -1/2 errors, right? Yeah. Okay. So repetition code is nice, right? Because first, of course, it's less qubits, but also because the classical code has a much higher threshold, right? The surface code threshold is 1%. The repetition code is around like 10%. And of course, the lower connectivity is also nice for the experiment, right? So to think about crosstalk and stuff like this. Right, so this is what I told you, right? How you measure the stabilizers. This is XX. If there's an error here, this 2 flag, and then node of error. And as I mentioned, we use these ancillary qubits, transmon qubits, to measure these repetition code stabilizers. Similar how people do for surface code, right? But here we just have to measure XX. And there's a key challenge though, right? And that's the idea, maybe the final idea I'll tell you in this presentation, which is because you're correcting errors separately, right? So bosonic mode corrects X error, and the outer code, in this case, the repetition code, corrects Z error. You have to be very careful because suppose that you suppress X error using your cat qubit, so that's great. But when you implement the gates, right, to correct Z errors, your gates are such that a Z error can become an X error, right? Then you're doomed because you're not correcting X error, the outer code, right? So you need your gates to be what we call like a noise bias gate. And this is like a special way of implementing gates such that the gates cannot convert a Z error into an X error. And I would say, well, but this is always the case, right? So a control NOT gate, a CX gate, if you look at the commutation, right, of Pauli's through it, you can see that, if you start with Z errors, you never end up in X error. But that's not enough because the gate is like a continuous process, right? It's really a Hamiltonian evolution, right? And the Z errors, they can happen during the gates. And then if they happen during the gates, you don't have this promise, right, of this commutation relation anymore. And actually, you can show that if you only use qubits, right, then it doesn't exist a bias preserving gate. It's like there's no go theorem, right? Or even any finite dimensional system. You can approximate, but it doesn't exist. So that's an interesting thing, very unique of bosonic modes, that you can have this kind of bias preserving gates. You can have them in in an idealized setting perfectly. But here, because we wanted to have something that it's not so hard to implement experimentally, we were happy just to get enough bias, and for that, transmon was enough, but we had to use more than a qubit. We had to use 3 levels of the transmon. So this was the idea. How implement a CNOT gate right between a transmon and a resonator? Well, it's kind of easy. The natural interaction there is like the dispersive interaction, right? It's something like this. So when there is a chi, right, a coupling, and when the transmon is in the excited state E, you have like this photon number operator on the cat, right? So the cat rotates in phase space. And of course, the F level of the transmon, the third level of the transmon also has a different chi, right? So the cat just rotates at kind of a different, right, rates. And now we're going to encode our ancilla 0 of the qubit as the ground states, and the 1 as the F states. So what will happen? Suppose the transmon goes from 0 to 1, right? Then the cat rotates, right? If you time for like time, pi over chi, right? So it implements the NOT gate. So this is the CNOT that you want, right? If it's in 0, there is no chi, nothing happens. If it's in 1 and you wait pi over chi f, you do this rotation. That's great. That's what you want. But now what happens if there is a decay, right? Suppose there is a decay during this process, and if the chi's were different, then you'll be in trouble, right? Because in the end you end up in a different position phase space that you don't want. But now there's a trick you can do. It's called like chi matching. And suppose we make we engineer this dispersive interaction such that the 2 chi's are roughly the same. Okay, and then we just do in design. We just design our transmon and to have this property. You could do actively as well, but we do in design. Then what will happen? So suppose you are trying to do that. There is a decay, right? You end up here if they are not chi matched. But now, okay, they are roughly chi matched, right? So then the cat is not too far, right? So because there was this dispersive interaction here, you went up to here. There was a decay. Now this is the dispersive interaction, right? Because the transmon decay to E. But now chi is roughly the same, so you end up, not too far from where you should have ended up, right? And then with the 2 photon dissipation, it goes back there. So what is happening? We are designing a gate which kind of like there's an error transparency here, right? So in the sense that one decay in the transmon does not lead to a logical error, right? So is the gate is robust to that, and that's this property that we want, right? That if there is an error in the transmon, of course you don't get any information, right? So if you measure this transmon, you won't learn what happened, but it doesn't disturb the cats, right? You don't have this kind of X error that you're afraid of. This bit flip error, right? Where you want to end up here, but you end up here. Okay. So this is, let me show you some data. So we did this experiment. Let me just show you. one thing instead, this one. So we did this experiment, right, where we do the two-fold stabilization, right, to correct X error. We run this repetition code many times. We collect the data. Then we look at the logical probability of error. And of course, we have a distance 5 experiment. We can do it with 2 distance 3 chunks as well, right? So we did it for this smaller distance 3 here on the left, another one on the right, and we did it with the distance 5, the whole chain. And then we computed the logical error rate here. And of course, we can vary alpha square, right? So we vary alpha square over this range from 1 to 3.5. We look at the logical error rate. We should always choose the alpha square that gives the best logical error rate, right? That's the optimal point. We look at it. Then it's like all around like 1.5 mean photon number. And then we found, right, that for the distance 3, the average was around 1.75% logical error rates for these logical qubits. And distance 5, it was a little bit better, right? So we saw a little sign that error correction is working here, right? How will be lambda here? If you want to talk about lambda, well, lambda will be slightly bigger than 1 here, right? Whereas the state of the art is in surface code is like lambda of 2, right? So you're not at the state of the art yet, right? But we saw error correction start to work. We want to get state of the art and maybe beat it. But the point here is that we have this approach that we think is more hardware efficient, right? If we can make it scale and work. All right. So this is just something that let me just mention this, right? So what we have to do to make it work, right? So we needed this tantalum resonator. It was very important to get the cat qubits to be good enough. We had to do this kind of three-dimensional, this flip chip process, right? To integrate the tantalum chip to the aluminum chip. We had to understand this buffer, right? This buffer, this nonlinear object that have the free-wave mixing, but it usually has some like kind of parasitic inductance that can be very bad. We had to understand how to handle this, and we have a paper where this is explained in detail. This frequency targeting was very important. It's exactly because we need the sky matching that I show you, right? The sky matching to work, we need the skies to be roughly the same, and we have to do that in design. So that requires some way where we could change basically the bottom chip once we learn about what was like the frequencies of the transmit in the top chip. And of course, there was a lot of design and simulation, right, to make this work. There was people working the 3Gs with a lot of wires, right, coming in. And of course, some control electronics right on the side too. So there's like definitely a lot of people involved in this experiment. All right, so let me just mention a few directions, like very briefly. One direction is that, okay, so suppose we want to keep improving this, right, to build a really good logical qubits. Maybe we can just increase alpha squared to a very big number and just have a bigger repetition code. That might work, but no, maybe at some point the cat qubit cannot really bring down the logical error rate to 10 to minus 14, right? Maybe there's some other process that we don't know, or something that we know that the cat is not correct to that level. Then we might want to go to this thin surface code that I mentioned, right? So this is experiment. So now we want to build a 2-dimensional version of the experiment that I show you, and just have a little bit of dx equals 3, for example, to correct also x errors at the outer layer. And for that we need a new type of gates, right? To implement the surface code here, which we have just this should not be here. It's another talk that I gave where people in the team were there. But all right, and we have some estimates, how eventually in this long-term goal we can have like some improvement in overheads, like roughly 10x over what we have for the surface code, right? So that's kind of the ultimate problem. We want to eventually scale, and of course we have to scale a lot, but we hopefully we have to scale 10x less than if we just do the surface code. There's even like a higher stakes, I guess, direction, which is this one, which is like, suppose actually that we just do the repetition code, right? Repetition cap code, as I show you. And this is some plot that we get, where we get like almost a second, like X protection, right? Just at alpha square, like, alpha square like 4. And then you can think, well, the cycle of error correction, the time to measure the gates and measure is roughly 1 microsecond. And the bit flip time, right? Once alpha square is like 4 or 5, it's like about a second, right? That we even see 10 seconds sometimes. Then what is the bit flip error, right? Per cycle is like 10 to minus 6, right? You can just do this estimates. And suppose really the gates are good, right? So you need better gates now, right? Just these gates that I show you are not good enough, but suppose you have a better gates, and we have some ideas that could reach the single cat qubit performance. So then bit flips, they will be like 10 to minus 6 error rates. And how about phase flip errors? They increase linearly with alpha square, right? The cycle is 1 microsecond again. And suppose we could get better resonators than we have today, right? Today we have like 70 microseconds. Suppose we could improve to like 300 microseconds, right? Which people see in 3 dimensions. In 2 dimensions is a challenge, but you know, we're trying to get there. Then you get like 1% Z error rate per cycle as well. And now, if you look at the surface code, you do the estimation, right? And look, and you think that it has this bigger threshold, which is very nice. You can find out they will be able to reach like 10 to the minus 5 logical error rates, right? And you know, Google state of the art is 10 to minus 3, right? So like 100 times better than state of the art today, with only like a distance 11 repetition codes. And we find this like an amazing result, right? So we do require the special gates that we are trying to, you know, we are evaluating if they can work. We do require better T1s, which we are also trying, but it's hard. But we do think that this is kind of like you know, it would be very exciting if we could do it, right? And it's something that we are actively working towards, right? So we are planning kind of for the worst that we have to scale with surface code, maybe with more hardware efficiency. But we are also trying to see if we can really push this idea such that we can have very, very efficient error correction, right? Just using repetition codes and get this strong suppression with mean photon number now bigger, allow 5 or 6 or 7, right? For the bit flip. All right, and then there's other ideas. You can do LDPC codes. You can do other things in quantum computation, for example, match state distillation. That is one of the components that you need in addition to logical qubits to make a quantum computer. And again, we expect some good improvements, right? If you have this bias noise. And with that, okay, I don't want to mention that. I think I'll stop here. Thank you very much.
Brandao, I think we have like time for questions. If you have questions, either here or from the online audience. So what are your questions? We have one here.
So I was wondering, I'm trying to understand the 2-photon dissipation process and how it stabilizes.
Yeah.
And I guess I was thinking like, if you have just the individual alpha or minus alpha.
Yeah.
Like basically all of your coherent states are stable under the 2-photon dissipation, right? But it's like when you have the superpositions that of alpha plus.
So you break that because indeed, right, this free wave mixing that I show you, right? Where you have like A square B dagger, right? And then B is a very lossy mode. This leads to some jump that will go as A square, right? But now you also add something else, which I should have written, I just said in words, which is a 2-photon drive. So you also have a drive. The Hamiltonian will be like, you know, some chi times A square plus A dagger square. And then if you combine them, you can find now that the jump operators of a master equation, they go as A square minus alpha square, where alpha is just a constant that depends on the 2-photon drive strength. Right? So maybe, well, actually I might have here when I show you. Here. So you know this is the jump operator, right? And now you can say, well, what are the dark states, right? For which states, if you apply this, it gives 0, right? And then you can see that then it's only plus minus alpha, right? Coherent states, right? Because you know A square applied to alpha minus alpha gives back alpha square, right, times ket alpha. But now you have this minus alpha square, so they cancel and it gives 0. So because you know, like how much energy you're pumping into your, right, with this 2-photon drive, you're pumping into your resonator, this sets alpha to be the particular value they want.
I see. So they're like with that master equation, it's basically like the 0, or the dark state is just saying that those are the only ones that where the derivative is 0, so that all the other states will be driven towards those.
All the other be driven. That's right. Yeah, that's right. And then you can show that if you sign one of them, you know, the probability of going to the other one that it could is exponentially suppressed, right? And then it becomes really just this, yeah, these steady states, and they stay there. Yeah.
I do have one more question. I was wondering with this, without stabilization, like what is causing the, like at these higher drive powers, what is causing that warping?
Well, it's many things like, there's all kinds of processes, like just photon loss, right? Well, okay, photon loss actually wouldn't cause, right? Because photon loss, you still have the coherent state, but we have, for example, actually this is mostly, the experiment is mostly self-current that we have there, right? So we also, we don't want to have, but we do have, right? Like naturally just, some A dagger A square term, right? And this will lead to some diffusion, right?
It's because your waveguide isn't perfect, or like what causes?
Yeah, because it's not completely linear, right? So if you was a completely just a harmonic oscillator, you have this A dagger A, right? This will be equally spaced, but there's always a little bit of non-linearity there, even if you don't want. Also because it's coupled to all the non-linear elements, right? So there's some hybridization, and then you always have curve. In our case, this self curve is like, try to keep it small, but it's like 20 kilohertz, something like this, and that is so this.
Yeah, so I wanted to go back to your matching chi condition in order to get
Right.
that degenerate error protection.
Yeah.
It seems challenging to get those chi's matched. Are you using a tunable transmon in order to like tune it after the fact to account for the geometric fluctuations in the fab? Is that what you're doing?
Right, it's a good question. And we could have used it, but we didn't use it. So we have fixed frequency transmons.
You're using fixed.
We do have tunable couplers, okay, to switch on and off the gates, but this doesn't really help with the chi matching, right? So then we in design we try to do the chi matching, and you're right that it's challenging because fab is very right. Unfortunately, it's not what we wish it was. But then we developed this strategy. I don't know if I have a picture, but it's the following. So you first fab the top chip, which is the aluminum chip where the transmons are, and then of course the frequency won't come exactly what you want. But then you try to compensate this. So you first measure what is the frequency of these transmons, right? You can do that at room temperature, right? And then in the lower chip, if you remember the cavities, right? They were, this bigger, right? So these were the cavity modes, these bigger things here, right? And then we adjust their size to change their frequency to match, the transmon deviations.
I see. So you do the transmon first.
Yeah.
And then you adjust the resonator in order to match
To get sky matching. Yeah. That's what
is interesting.
Yeah, that's where we end up, right? We try many things, but that's where we end up. The kind of
And
works.
because the resonators are bigger elements, the fab tolerances don't affect the
And
precision.
that is right, and also because they are linear, right? Usually the just for junction is the culprit, right?
Yeah, exactly.
And because they're linear, it's more precise, and also they're bigger, it helps. But yeah,
This is a benefit of the flip chip design I never considered. That
it
you
is.
can-
Yeah,
You can measure or build half of it, measure it, and then build the other half to match it.
that's right.
nice.
That's right. Yeah,
That's nice.
we also it was we try and make other things for like more than a year, and then eventually.
Yeah, this
This
is why
one-
I was asking. We've dealt before with trying to match chi's, well, even on different devices, and
Right.
it's not simple
It's
to
not.
get
I know,
them matched
yeah.
geometrically.
Yeah.
so.
There's a way right now you can also use a higher level of the transmon, and then you can have like a off resonance drive there, and that's a way to actively chi match.
Yeah.
But it did not work in our chip. We had some anomalous heating when we tried that, so we
Yeah.
could never make that work. Yale tried that and it worked in some single bosonic mode experiments, but we had to go to this other approach.
Right, since you have multiple transmons here, I guess you can match each of the dedicated resonators, so without the need for all these extra drives. So
That's right.
That's very nice.
That's right. Yeah.
Okay, more questions? Gleb from
Oh.
Zoom.
Okay, just I wonder, it looks like all the story depends on the mean photon number. So it looks like the more photons you have, the more controllable qubit and algorithm you have. And how you can, which physical parameter controls the number of photons? Because it looks like if you have few photons, that the system becomes less controllable, and probably that's why you need like additional sources of photons which you borrow from photons to correct errors. Is it a sort of correct understanding or not, but
Right.
just,
So,
just
oh, sorry. Yeah, that's right. So first, right, the number of photons that you have in the resonator, that you can control by just how much 2-photon drive you put there, right? So it's just like how much energy you pump into the resonator. So alpha square can really vary, and there is a single cat qubit experiments with alpha square up to like 100 photons, and we haven't got this at AWS, but like people in France, they do that as well, and they got with alpha square, I don't know, I forget, like 20 or something like this. They now have hours of bit flip lifetime, right? So really, it seems that the sky's the limit there. People keep getting more and more. But that's not the full story, right? Because indeed, the more photons you have, the better the system is, but just for bit flip errors, right? But there's this price you pay, which is more phase flip errors. And then you need, this outer code to correct for phase flip errors. And now there is a trade-off, right? So of course, you don't want to be above the threshold of the outer code, because if you are, then simply cannot correct phase flip errors. But you don't want to be too close to the threshold as well, right? So you want to be substantially below the threshold for the outer code, and that gives like a maximum value of alpha squared, right? That they can use there, and then you end up in this plot, right, that I show you, right, where for different values of alpha squared, you can look at the average. You can look at logical error rate, which is the average of the bit flip error rate and the phase flip logical error rates. And then you find that there is an optimal value of alpha, right? And that is the alpha you should use, exactly because you are balancing bit flip protection and phase flip protection, and one gets better with bigger alpha, but the other one gets worse. I hope that.
does it look like you should balance between quantum interference and coherent time, the time of coherence. So if you have many, in other words, if you have many photons, then quantum superpositions should be lost, just because.
Yeah. That's exactly right, and that's kind of this linear increase of z errors, right? The z errors is exactly the phasing, right? The superposition is getting lost, right?
And on the other hand, if you have few photons, then the system becomes less controllable by classical parameters.
Yeah, I don't know if less control, but it has more bit flip, right? Bit flips are more often there, right? So alpha becomes minus alpha and vice versa more often, right? That's maybe that's what you mean, but that's exactly what happens, right? So
I just try to understand the limits in which such model works.
Yeah. Yeah, I didn't understand the controllability part, but yeah, what you said about the coherence is definitely true, right? And alpha square cannot be too small, because then you're not correcting bit flip errors, right? Which you have to, right?
Just ask another question.
Yeah, so you showed this actually this slide, this most recent data. Your D equals 5 code. How many cat qubits did you have running concurrently there?
5. Right.
Five cat qubits. And each of them has a 2-photon drive on it.
That's right.
Are you battling any heating issues in the fridge because of all the drives?
Yeah, that's right. And no, we haven't seen. We are like in this like 20-30 millikelvin. We haven't.
So far it's okay, even with 5 stabilizing drives concurrently.
Right, and heating is indeed a limitation here, right? We definitely, because of like this gate that I show you, right? So if there is a heating from ground to E, that's kind of leads to a bit flip error, right? So definitely heating is like has a first order effect, but of course heating is kind of the time of heating is much smaller. The time of heating is much bigger than T1, right? Because it's like thermal population factor, right? And thermal population, the temperature we are is like less than 1%. So it's longer, and we haven't seen this is consistent with the temperature that we at, the heating rate that we see of the trend.
That's encouraging.
So we haven't seen like extra heating from these drives.
That's encouraging.
Of course, the mean photon number is like 1.5, right? So it's kind of small, right? So maybe if you go to like this 10, which maybe want to go one day, it might be different. This I don't remember if we have data on that one.
Makes sense. And I do have one more kind of maybe mean question. You have outlined a plan to get to the 10 to the minus 5 error, right? With
Yes.
this, with what, a d equals 11 code?
Yes.
Which is great. Do you have a plan to go the other 9 orders of magnitude? Right.
Good question. So you know, I thought that that would be very, very hard, right? And maybe it will be, right? So we'll have to learn. But if you think about it, right, this was assuming this 1 second, right? And now, you know, like Alice and Bob, right? They are a company in France. They also do similar approach. They have measured, what was the last thing? They have measured with alpha square like 8 or 10. I want to remember correctly, like 17 hours, I think. So you know, this gives, right, like 5 orders of magnitude more, right? So we're not there yet, but you know, it's really getting, we don't know what is the limit, right? So of course, it's very challenging to do that with this kind of coherence limit CXK, right? This is really where the crux of the matter is. We are working on that. Even to get this 10 minus 5 we don't have yet. So maybe that will be very hard. And that's why I think eventually, you know, like I do think that you'll be able to get some leverage from this, right? I think this should have. I'm hoping this will be possible. 10 to minus 14 maybe is too much, but it might be, given the single capital that you already have, right, which is like many hours. I think, you know, if you just put the same thing again, you might be able to reach, right? Maybe you could reach 10 to minus 9, 10 to minus 10. But then I think eventually, right, when you're there, you do want to, maybe you have to go to that eventually, right? Because just for distance, dx equals 3, you square the logical error rate, right? So if you don't get 14, you only have to get to roughly minus 7, right? And then you're there. So I do think that indeed, it's like eventually you might have to go there, or you have to get this astronomical long bit flip times, right? And very good gates, which we'll have to see where we end up. But I'll be quite surprised if we can go to 10 to minus 14, right? And nothing happens. Probably things will happen.
Assuredly hard, but it sounds like there are possible routes.
There is,
in
yeah.
Principle, yeah,
That's right.
good.
On that slide with 3 energy levels.
Yeah.
Yeah, what is the distance between these energy levels in numbers? I'm just
Right. So it's like it's a transmon and the frequency for this experiment, I think was about like maybe 5 gigahertz.
5
So here's 5 gigahertz, but of course it's a transmon, right? So it's non-linear. So this is 5 gigahertz, and this is 5 gigahertz minus the non-linearity, which is like 200 megahertz.
5 gigahertz is not number. Okay. Thank you.
More questions? So let's thank our speaker again. Thanks, Fernando. I don't know, when do you leave?
I have time to, yeah.
Yeah, I mean, so he'll be here. So if you wanna chat, I think that he's available.
Yeah, for sure.
I think so.